Well, good afternoon, everyone. Welcome. Welcome to the McCoy Distinguished Lecture this afternoon. And this is the third and final award lecture, and it has been a really exciting day to hear such fabulous presentations from our award winners that we've recognized today. It's just a day of reflection, a day of celebration for our distinguished faculty and researchers here at Purdue. And I think, we are often caught up in the day-to-day work that we do, and it's just, I think, an important time to reflect on our accomplishments. So thank you all for being here with us this afternoon. My name is Teresa Mayer. I'm the new Executive Vice President for Research and Partnerships, and I started on August 1st, so I'm just finishing up 3 months back here at Purdue, and it's been a real privilege to participate in this event and really just continuing to get to know, listening and learning about the Purdue community, and I hope that all of you look forward to the presentation, the McCoy Lecture this afternoon. This award was established in 1964 by Mrs. Ethel Terry McCoy to honor researchers in the national sciences who have distinguished themselves among their colleagues. The McCoy Award winners are nominated by their peers, and they're approved by the EVPRP, as well as the president of the university. So this is the 54th Distinguished McCoy Lecture. And I'd like just to take a moment to recognize all the past McCoy Award recipients who are attending the lecture today. If you could please stand so we could recognize you. So there should be many. I would also like to invite you after the lecture to a reception that will be held in Stewart Center's Robert Ringel Gallery, which is just to the left down the hall. So I hope all of you can join us for some light refreshments after the lecture. I'd like to, at this point, welcome to the stage Distinguished Professor of Physical Chemistry, Dor Ben-Amatz, and I'm sorry, I've mispronounced your name. As a co-nominator of this year's award, he will introduce this year's McCoy awardee, Sabri Kass, who is a professor of chemistry here at Purdue.
Thank you, and it's really a pleasure to be up here introducing my friend Sabri Kass. We actually, in some ways, were friends even before we met. I was a postdoc with Dudley Hirschbach at Harvard, and then he was later a postdoc with Dudley Hirschbach before we came to Purdue. And I was part of the committee that hired him here at Purdue, so it's just been wonderful to see his career evolve as it has so wonderfully. As many things I could say about Sabri. I've known a lot of theoretical chemists in my day, both in my generation and older than I and younger upcoming generation. And it's really fair to say that there is nobody that I've ever met that has got the sort of creativity in the sense of thinking way outside the box that Sabri does. He's just fearless about going into territories that nobody imagined before. He was doing this since the days he was an assistant professor, where he developed algorithms for things ranging from global optimization, algorithms for finding global minima of potentials that are very complicated landscapes. I don't know how much you know about this problem, but it's got lots of applications in biological modeling and other areas. Simple molecules have simple potentials. It's easy to find the minimum, but as soon as you put a lot of atoms together, it gets very hard to figure out how the landscape looks. And he did that. Even more interestingly, I think he developed algorithms that are called finite scaling algorithms, and that basically utilize an analogy between electronic structure of atoms and molecules and macroscopic phase transitions, like the transition from a liquid to a vapor or a solid to a liquid, where suddenly at a certain temperature, the system transforms and freezes or boils and evaporates. And Sabri realized that the same mathematics could be used to describe the stability of electronic states of atoms. Like if an electron or anion is stable under certain conditions, depending on the nuclear charge of the atom, this anion will suddenly become unstable and ionize. And the mathematics underlying it is completely analogous to these phase transitions, but instead of temperature being the knob that you turn to transform one state to another, it's the charge of the nucleus. But as another mark of his creativity, he doesn't just stay with one thing, he's on to another horizon. And after being promoted to an associate professor, maybe even a little bit before that, for about the past 15 or more years, he started thinking about something that has now become almost a household word, which is quantum computing. But this was in the day where nobody knew that term. He was one of the leaders in thinking about how to, if you had a quantum computer that instead of being made up of binary bits with on or off states, is made up of qubits that can be oriented in any direction and have a state that is a superposition of an on or an off state, so it contains much more information. For example, if you had a quantum computer with 100 qubits, which just a very few years ago was a pipe dream that people thought would never be realized, but now exists already, that computer can have, is equivalent in its ability to hold information to something like 10 to the 50 conventional bits. That's about the number of atoms on Earth. So obviously you can never make a conventional computer as big enough to hold the same information as a 100 qubit quantum computer. Anyway, without going on and on too much long-windedly, and you're going to hear more of this story from Sabri, he was the first to think about how you could use a quantum computer, if it was ever made, to solve chemical problems, to solve the Schrödinger equation, the electronic structure of atoms and molecules. And he wrote algorithms that could be implemented on these non-existent computers if they were ever made. When I first heard about this stuff, I was thinking, wow, this is fascinating. Sabri's going somewhere else again that I'd never thought about. And I really had the gut feeling that this is, interesting academically, but I was not sure this was ever going to be made. But then in 2010, he was the PI on a big grant from NSF called Center for Chemical Innovation, the first such grant to fund research on using quantum computers to solve chemical problems, again, before these computers existed. They were very successful. They wrote lots of algorithms, produced PhDs. Many of those PhDs are now leading research programs at Google and IBM and Microsoft that are doing this stuff. But ironically, usually in an introduction like this, you wouldn't mention things that are not just the successes, but this phase 1 CCI project was funded, and it was denied for phase 2 funding for a very interesting reason. They said, well, there isn't a computer that can actually implement any of these algorithms yet, so they're not sure that any of this is really real. Since then, all this stuff has happened, and the algorithms that they wrote during that CCI, and since then are now being implemented on quantum computers. You're going to hear more about that from Sabri. And there's huge push to hire people who are doing QIS. Search is hiring many faculty in the area of quantum computing and information. And Sabri is playing a leading role in that. He also got recently a very big grant from the DOE to do more quantum computing and applications to chemistry. So with no further ado, please join me in welcoming Sabri.
Thanks, Bob. Thank you. Thank you for the beautiful introduction. I'm deeply honored to receive this award. And today I'm going to discuss the quantum information and quantum computing for complex chemical systems. And this is an exciting and interesting time for the field of quantum information and quantum computing. And if you saw the news from last week, or just October 23rd, Hello Quantum World, Google publishes landmark quantum supremacy claim. And in this claim, the Google Quantum Computing Group, with their chip with 53 qubits, simulating a random quantum circuit in 3 minutes. This one. And they claim that if you do this computation on the fastest supercomputer, it takes 10,000 years by extrapolating the information, of course, from small computer to large one. At the same time, IBM came up with this article saying not so fast. If you do careful analysis, it takes 2.5 days to do the same computation. So whether it's 10,000 years or 2.5 days, this is really an exciting time for quantum computing. And just to explain, the quantum supremacy means that a task that a quantum computer can do and no supercomputer can do the same thing. And then you see the news goes on, quantum supremacy, the gloves are off, and this is by Scott Ellison, who is a theoretical computer scientist at Texas A&M, at University of Texas, Austin. So I'm going to explain to you this field so you can see what is this fighting all about. To do that, I'm going to explain what is quantum information, what is quantum computing, and then focus on quantum chemistry. And you will see I'm going to use the word quantum a lot of time in this talk. So what is quantum all about? We all study in high school classical Newton's equation of motion, describing how the stars move. And then by the beginning or the late 18th century, the beginning of the 19th century, there were a couple of experiments that cannot be explained with the classical physics. And in particular, the structure of the atom. And as we do in science, if we cannot explain experimental results with the old theory, we have to develop a new theory. And we have seen the development of quantum theory. And many scientists were involved. Planck, Einstein, Bohr, and many are. But our hero today is Schrödinger because we can use his equation, which is generalization of the Newton's equation of motion for elementary or subatomic levels. And here, quantum mechanics is explain the nature and behavior of matter and energy on the atomic and subatomic level. So you can see this theorem, we have it for 100 years. And so far, there is no single experiment that contradicts the theory. So we can say, okay, the quantum mechanics is the theory that we have with us. But how this is related to computing, which is our main subject. Then Feynman, his famous lecture back in 1982, he said, the quote, "Nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical, because this is the theory we have." And back in 1982, this was the Feynman proposal, creating machines based on the laws of quantum mechanics instead of the laws of classical physics. And for us, since the discussion will be application in chemistry, we know that quantum mechanics underpins all of modern chemistry, and this is the relevance of this proposal to our field. Now, if you go back to classical computing, it is really impressive when you go from the early computing of computers filling a room with 30 tons, all the way down, we have laptop and smartphones. So shrinking the devices and make it more powerful. And if you look at the number of transistors, it's really astronomical. We talk about billions of transistors in a computer chip. And you can see the scale. You can see, okay, where is this going, the scale? Of course, we're going to atomic and molecular scale. And when you say what is next, you can continue with this. And every time you have a problem, you try to solve it. The other option to go to quantum computing. So, okay, what is a quantum computer? As mentioned by Feynman, a computer that used quantum phenomena. So quantum computer, a computer that make direct use of quantum mechanical phenomena, such as superposition, interference, and entanglement. And I'm going to explain these phenomena, what is superposition means, interference, and entanglement, and how these phenomena are used in computing. So again, just to compare with a classical computer, a computer that uses voltage flowing through circuit and gates, you have on and off. And this is what we have for the last 70 years. Okay, let's start with the superposition. What superposition means? If you talk about information carriers, encoding classical information, you encode it in classical bits, 0 or 1. And if you think about it in two-dimensional vector, the vector pointing up, 0, pointing down, 1. So all classical computing with all the development is based on binary system, 0 or 1. But in quantum mechanics, we know, for example, the electron could be in two places at the same time. So if you have a quantum system with two levels, 0 or 1, in quantum mechanics will allow you to make superposition, which means you take 0 plus 1. And of course, this is allowed because quantum is a linear theory, and you can do the sum. Which means in this picture, you can rotate your vector not only up and down, you can rotate in any direction. So if you take it in this direction, you have a superposition of 0 and 1. Again, superposition, because we have waves, this allows us to make a sum, or the electron or the particle that we're using will be in two places at the same time, and we call this quantum bits or qubits. So this is the superposition. Now, what about interference? So interference, this is the famous two-slit experiment. You have two openings, and here you shoot with electrons. And people repeated this experiment with atoms, molecules, even with buckyball. And they look at the screen, and you will see bright and dark regions because of the interference, since you have two waves, and they interfere in this screen here. So interference means you do a superposition. So if you do it in phase, you have constructive interference. And when you do it out of phase, you have destructive interference, and you see nothing, or you see higher, you increase the amplitude of the intensity. So this is the interference. Now you can ask, how do you use interference in doing computation? So for that, I would like to we modify this contour, a cartoon to show how interference works. Suppose I'm looking for the phone number of Professor Durbin Amot. So how I do that, I take a phone book and start going through number by number until I reach his phone number. So I go searching all the entries until I get to this one. Suppose I would like to do the search quantum mechanically. Quantum, so I will encode the information and do the search all at the same time. So we have superposition of all possible paths. So I will do it all at the same time. Now you ask, okay, what is the interference in this experiment? So the interference is really a tricky part of the whole computation. This is where really the hard work is. You have to design your algorithm in a way that the constructive superposition will lead you, constructive interference will lead you to this answer, and the other will be like a dark state, will be destructive interference. But this is the hard part. And the way it works, again, you can see it's all destructive except this one was a constructive interference. And this is how interference comes into quantum algorithm. It's a very tricky business, but if you can design your algorithm in a way to take advantage of the constructive interference versus the destructive interference, you can get the answer, especially for quantum search. Okay, as in classical computing, we have a classical logic gate, which you give strings of zeros and ones. They manipulate it to do a certain computation. We have the same quantum gates or quantum logical gates in quantum computing of the qubit. Because if the qubit pointing up or on this direction, we know how to rotate this in any direction we want. And this is called single qubit gates. And we need also two qubit gates. This is called control NOT gate. So the control will not change, but if it's 0, you do nothing for this. And if it's 1, you flip the target. And people have shown that the control NOT plus the single qubit gate are universal, which means you can do any computation with these quantum gates. So we have quantum logic gates as we have in the classical computing, and with the initial state, you can run these logic gates and do the computation. Now, if you look at the qubit space, so we work in quantum mechanics, we call it Hilbert space. So we have single qubit, you have 0 and 1. You think about it as two-dimensional vector, 1, 0, 0, 1. Now, every time you add one qubit, you double the space. I add one other qubit, and I double the space. From 2, I have 4, 0, 0, 0, 1, 1, 0, 1, 1. And if I have n qubit, look at the space, it's 2 to the n. It's a huge space. And again, we can do any arbitrary combination as we did with the search. And any operator in quantum mechanics, you can present it as a matrix, 2 to the n by 2 to the n. And you will see later, we decompose it into quantum gates and run the algorithm. Just to give you an idea about the number of qubits, this is where the threshold. If I have 50 qubits, I have a space 2 to the 50. This is the limit of what we have today with the supercomputers. So if I have a quantum computer with more than 50, we can start doing tasks that cannot be done with a classical computer. So now in chemistry, if we have a large number, we said, oh, we have Avogadro number, which is 10 to the 23. Avogadro number is 80 qubit. If somebody builds a machine with 80 qubit, you simulate Avogadro number, which is really huge. It's a big number. And of course, if we have 300 qubits, 2 to the 300, you have more states than atoms in the whole universe. Now, if you look at the history of quantum computing, after Feynman, David Deutsch at Oxford, he showed how quantum circuits are universal. And then we have the famous or popular algorithm by Peter Shor. He showed how quantum algorithm can factor large numbers in a polynomial time, where the best known classical algorithm is exponential with the size of the number, with the number of bits. And then Grover put his quantum algorithm for search with a quadratic speed up. And Seth Loy talked about universal quantum simulator. And if you look at the dates, we have 30 years if you go back, we have 30 years of research. So what is the excitement? Why now? So the excitement, because in the last few years, which I will show you in a minute, it has evolved toward industry. And we see all the big companies are investing heavily in this field of research. So what are the requirements we need to build a quantum computer? So these are obvious criteria, and you have a well-defined 2 quantum system with 0 and 1. Scalability, if we have 1 qubit, you will be able to scale it to more qubits. You have to be able to initialize the system, control it with the quantum gates. And what killed this field for the progress was not done in this field because of the stability, which is the decoherence time. Because these are very fragile systems and interact with the environment. So you have to be able to separate it from the environment while you're doing the quantum computations. But now people have ways to really do this and enlarge the coherence time so you can run the sequence of quantum gates. And at the end, you have to be able to do measurements of these devices. So over the last two decades, people developed many platforms, starting with optical quantum computer, where the qubits are the horizontal, vertical polarization of the photon. Trapped ion, you encode the information in the state of the ion. NMR, you can think about the spin pointing up and down as a qubit. The superconducting loops are wires with a superconductivity that the current go without resistance. You think about it clockwise, anti-clockwise as a qubit. Also quantum dots or polar molecules in an electric field. There are many platforms, but the 2 leading platforms are the ion trap, encoding qubits in the state of the ion, or the superconducting qubits. So back in 2016, IBM put the 5 qubits, and they called their IBM Quantum Experience. Anyone can open an account and experience their design for a qubit and run it on their machine with up to 5 qubits. And then they went to 16 qubits. And in 2017, they announced their 50 qubits chip. And just in last month, they put together the 53 qubit quantum computer. At the same time, Google, last year in March meeting, they announced their 72 qubit chip. So you can see the progress only in the last few years, went a few qubits into numbers like 72 or 53. So you can see now Intel also got into the race, and they have 49 qubits. And the IonQ, they have also a company which started at University of Maryland, and also they have more than, it's between 50 and 100 qubit. Earlier, we have also a machine. This is not universal machine. This is a machine for specific task, which is optimization or quadratic optimization. And they went up now to 2,000 qubits. And now the engineer, they're talking about the new chip with 5,000. They doubled this number of spins. But we call this quantum annealing machine because it solves only optimization problem. And I will come back to this machine later on to show you how one can use it to do electronic structure calculations. Okay, so we don't have to worry only about the number of qubits. Now we said IBM 53, Google 72. We have to worry also about the quality of these qubits. I mean, a little noise can destroy these qubits. And we distinguish between physical qubit that we are mentioning before, like these numbers, and the logical qubits, where you do error correction. So you have to worry about the quality, like the qubit gate fidelity, the 2-qubit fidelity, readout, and the decoherence time, T1 and T2. And you have to worry about the speed and the connectivity. So a lot of effort works in, developing solution for these kind of problems, and the IBM called this one the quantum volume problem. So what I described was on the hardware. In the software, there is a lot of algorithms for the last 20 years, starting with Shor algorithm for factoring, Grover for search, adiabatic quantum computing, and quantum walk, phase estimation, and you ask, okay, what else is there? And if you go to the website, Quantum Zoo, administered by Stephen Jordan, he was at NIST, and he moved now to the Microsoft group. You have, I checked for last year, they have over 60 different algorithms. So if you try to develop a new algorithm, it's better to check with the Quantum Zoo because they have a lot of documented algorithm with references and what the algorithm is doing and the scaling. Now, when we talk about quantum computing, there are 4 different universal ways. Universal means doing any computation. The quantum gate model that we just mentioned with IBM, Google, IonQ. There is also one-way computing, which is mainly starting with entangled photon, and then you do the computation as you go, the measurement. And every time you do measurement, the system collapses, and this is why it's called one-way. And then you have adiabatic quantum computing. You start your calculation from a known solution, and then you evolve it with time to get a new, to the solution of a new complex problem. And of course, we have topologically quantum computing, and here at Purdue, Mike Manfra is working with Microsoft to build this qubit with encoding in the topological stage of matter. Now we can see there is a shift in the research, how to build this quantum computer into what to do with this quantum computer. And John Preskill from Caltech, he introduced the concept, the NISQ era, which means noisy intermediate scale quantum computer. And you can see we have computers with 50 to 100 qubit, 100 quantum computer. And the question is what to do with these computers. Can we solve problems with this noisy computer and show that, for example, you can come up with a problem that you can solve it with these noisy machines that cannot be solved with a supercomputer? Now, in our research in the group, we were focusing on different problems. We're focusing, and I will mention a couple of these problems here, the electronic structure calculations. We also involved in algorithm for big data analytics, open quantum dynamics. I mean, the system interacts with the environment, so you don't have isolated system. We talk about also quantum coherence and control, entanglement in chemical reactions. And as Dor mentioned, also we did finite size scaling and quantum phase transitions. And now we can run this calculation on a quantum computer to show these different phases. And I will end with the quantum games for quantum education. So as Dor mentioned, back in 2010, we have NSF CCI Center for focusing on quantum information for quantum chemistry with my colleagues who are all expert and leading the field and still doing beautiful work on quantum information for chemistry. But we have 3 objectives. The first one, to identify the role of coherence and entanglement in chemical reactions. The second about building quantum algorithms for chemistry problems, and the third one was more on the hardware and error corrections. Now, in chemistry, still, the electronic structure problem is the heart of chemistry. And if we go back to what Dirac said in 29, quoting, he said, the underlying physical laws necessary for theoretical understanding of the whole of chemistry are known. Unfortunately, the difficulty is only that the exact application of these laws leads to equations much too complicated to be solved. So we know the equation that we describe how the electrons interact with each other, how the electrons interact with the proton, and the difficulty how to solve these equations. And of course, if you get the structure correctly, you can get the forces between atoms. You can build the potential energy surface, how the atoms move on this potential energy, and do the dynamics. And if you have the structure and dynamics, you will be able to look at complex problems in chemistry, like complex biological system, catalysis, drug discovery, material design, global optimization. All these problems are very complex and cannot be described, or you cannot do computational with the supercomputer. So what people do approximation or to see the trend in these systems. And of course, the hope maybe with a quantum computer will be able to do large calculations that we cannot do with a classical computer. At the same time, you can see, okay, this field is not new. People are working for 80 years and great minds, and there is a lot of advancement in the different methods. From ab initio, semi-empirical, density functional, and non-conventional methods. And you can see we have a couple of Nobel laureates. I mean, Jean Babel did get his Nobel for developing the wave function, Walter Kohn for density functional, and I did not include Karplus, and others also did research related to electronic structure. And the question is, what else? Why do we need a quantum computer or methods to solve electronic structure where we have this advancement in the methods and we can simulate maybe thousands and millions of atoms? And the answer is chemical accuracy. If we are going to achieve chemical accuracy, which is a 1 kilocalorie per mole, and you would like to do a systematic calculation, the computational cost grows exponentially with the size of the system. So this is why the hope maybe with the quantum algorithms, the computational cost will be polynomial with the size of the system, and we can go for large calculations. Now, when we talk about the quantum simulations, you have initial state, the input, you have your output, and all we are doing with this quantum computation, we're changing the classical processor to a quantum processor. So here where you put the quantum algorithm, and again, in quantum mechanics, you are not supposed to watch what's going on here because the minute you watch, the system collapses. So all this interference, superposition, all the phenomena, it will be in this black box. So you have to design your algorithm in a smart way to get the right answer when you do the measurement at the end. So without going into the details, to solve the Schrödinger equation, we know how to map it. First, we start with differential equation, we go to fermionic, and we map it to qubit space. So we know a systematic way to map Schrödinger equation into a quantum computer and read the ground state or the spectrum of the system. So just like to illustrate the idea, once we have a Hamiltonian here for a given molecular system, in a basis set, you end up with a matrix. And then you have to decompose this matrix into a sequence of quantum gates from 1 qubit gate to 2 qubit gates and run it on a quantum computer. For example, this is an example of the quantum circuit for H2. You have each line represent a qubit, and these boxes are the quantum gates needed to simulate that system. So the quantum algorithm we use to get the energy called the quantum phase estimation algorithm. And the picture of this one, the overview how this works. So you present your system, let's say within qubits here, and you do Hadamard to put all the qubits in a superposition. So the way the quantum algorithm works, you imagine what you are doing until this point is a quantum Fourier transform, not the classical. This is the main thing here. We're doing quantum Fourier transform. And this is where the speed up comes in. And once you do the quantum Fourier transform, then you do the inverse to read the phases. And this will give you an idea about the spectrum of the system. Okay, let's summarize what we have so far. What did we achieve in this gate model? So we have theoretical and experimental results for a small system like H2, water, lithium hydride. And the experiment ran from 2 qubits with the early optical quantum computer to 60 qubits with the IBM machine. So now we have experimental results with 60 qubit to just the proof of concept that one can, in principle, do electronic structure calculation for these simple molecules. And I like this analogy because back in the 50s, when we have the classical computer, and pioneer like Boyce, Shavit, and others, they were doing algorithm to solve the same problem, H2, H water, and this system on a classical computer. And now, 60 years, we see IBM with the 6 qubits, they're doing similar results. So we're still at early stage of doing this calculation, and hopefully we can learn from the development of this algorithm on a classical computer to apply it on a quantum computer. You can say, okay, now how do we move from this one? We can wait to solve the quantum volume problem, increase the number of qubits. I mean, making the circuit a shallow circuit and the architecture or quantum error corrections. But you can see that the hardware improvements alone is not enough. So what people in this field, they're trying to come up with ideas to use the existing machine to solve problems. And there are a couple of different directions. One popular approach is to use what we call hybrid, quantum classical. What is easy to run on a classical computer or not in classical computer? What is hard, you run it on a quantum computer, and you combine the results. And this is where IBM is pushing their applications. The other direction is to use the adiabatic quantum algorithm, and I will explain this in a minute. Or using quantum machine learning, and I will show a couple of examples about quantum machine learning. And also works on the QLED space. Instead of 2-level system, you can have many or D-level systems. Or use programmable quantum simulator. Many groups, especially in the optical lattices, they can but for example, there was a paper by 53 qubits and simulate a particular problem, not a universal machine. Now, in our group for electronic structure, we use the gate model with the QDate. I explained it. We have the adiabatic machine and the quantum machine learning approach. In the adiabatic quantum computing, the idea you start with a simple Hamiltonian that you know the answer. So you start with a problem that you know what to do with it. And then you evolve the system slowly enough to go to your complex problem, and slowly enough in order to stay in the ground state. You don't want to jump in the excited states. This is why we're doing adiabatic. And there is a quantum theorem said if you do it slowly enough, you stay in the ground state. We will go back. But you can see here in the example here, the complex system, what we call in physics the Ising Hamiltonian. It's a quadratic optimization. These I, they represent the spin. You have two spin interacting with this coupling, and this is local field with the spin. So if you can map your system into a spin type or an Ising type Hamiltonian, then you can use this machine to solve your problem. And this is where the D-Wave, they have 2,000 interacting spins. And of course, they sold 3 machines to Lockheed Martin, Google with NASA and NSA, and the machine is very expensive. It's about 15 million. Now, last year, we succeeded to start with electronic structure Hamiltonian and map it to an Ising type Hamiltonian, which was an interesting transformation. And the basic idea, you start with electronic structure Hamiltonian and you increase the space in order to be able to map it to Ising type Hamiltonian. And once you have an Ising type Hamiltonian, you can run it on this machine, and my students run it, and we can see how to get electronic structure calculations on this special machine. But for me, what is more exciting with this transformation, if you go back to Ising model, again, Ising developed the solution for one-dimensional system back in 1924, which was his PhD thesis. And this, again, used in statistical mechanics for almost 100 years to describe magnetic system or different phases, very complex phase diagrams. And the question is, when we do electronic structure, we map it to Ising, and we see all these complex phase diagrams. What is the equivalent of this electronic structure is still an open area, and will be exciting to see what is the analog of these phases in electronic structure. So what we have done in the past, we show that when you have ionization, when the electron leaves the atom, it's a true critical phenomena. Because we say we have ionization, but if you do the fundamental physics, you see that the way the electron goes from bound to continuum, it's a true critical phenomena, and we calculate a critical exponent, and we show it's a true physical system, true phase transition. But now we have an opportunity to go to Ising and see what is the equivalent of symmetry breaking in electronic structure calculation with these phase diagrams. Now, with the machine learning, I mean, it's a growing field in computer science, and the idea is like to have data to train the computer and to be able to predict results. And it has application in many different areas, like in solar farm, optimization, drug discovery, space, the stability of the grid, finance, and self-driving cars, all involved in machine learning. And probably the best application of machine learning is the self-driving wheel machines here at Purdue. So now we can ask, what is quantum machine learning? Quantum machine learning, we're trying to merge the two fields of quantum computing with machine learning. So we go to the machine learning algorithms when you have a classical machine learning, and we try to replace it with a quantum for speed up and trying to reach large data. So quantum machine learning is really developing game-changing quantum algorithms to perform machine learning tasks on large-scale scientific data sets. So for us, we focus on electronic structure calculations, and we have shown that the Boltzmann machine can do electronic structure calculations. And the way this machine works, you have visible layer, and now here we're working only with the qubit space. So you have the visible layer and you have the hidden, and in any network you can have more than one hidden layer, and we worry about the phase of the wave function, so you have also one node for the phase of the wave function. So the way this machine works, you sample from Boltzmann distribution. So the Boltzmann distribution, you sum over all the other variables, like the hidden variables, and your Boltzmann statistics will be as a function of local field and the coupler and the fields here. So now the cost function that we optimized is to optimize all these parameters to minimize the energy. And we were able to show that Boltzmann machine can be used to do electronic structure calculations, and we have results for these simple systems that I mentioned before. So you said, okay, what is the quantum on this one? The quantum, we built the quantum circuit to sample the Boltzmann distribution. Again, another development in quantum machine learning, we have also hybrid quantum classical neural network, as in the hybrid classical quantum for electronic structure too. Here, what is easy on a quantum, we do it in a quantum, and what is what's difficult in a quantum, and the easy part will go to the classical, and we can combine classical layer with the quantum layer to do calculations. And we have shown also this one can lead, and one can use it to do electronic structure calculations. The last area of quantum machine learning, we're doing also quantum clustering algorithm for classification of data. And the idea is to cluster the qubit here, and we developed the quantum circuit which allow you to map and rotate the data in a way that one will be down here and one be up, so you can read it at the end. And we use it to classify the quantum a phase diagram of the vanadium oxide. It's a very rich phase diagram. You go from insulating to metallic. So we trained the machines in the two different areas, and my students were able to reconstruct the whole phase diagram. Now, when we talk about quantum computing for open quantum system, in the group we have done a lot of work related to how birds finding their magnetic north. It's a very exciting problem. The Earth magnetic field is half Gauss, and still it's a surprise how these finding their magnetic north. And it's still an open problem. It's not clear how they benefit from this half or how they interact with the half Gauss. The other problem is the photovoltaic. And the idea here to see how quantum coherence can enhance the efficiency of solar cell. And for photosynthesis, try to understand the energy transfer. So all these problems are involved, the system and environment. And the question is, how do you deal with this one in a quantum computer? So if you look at the physics of these three problems, they all start with the sunlight. And you turn in photosynthesis sunlight into chemical energy. The solar, you go from sunlight to electrical energy, and sunlight here to direction. And when you try to formulate this problem by looking how the system is changing, and you integrate all the degrees of freedom of the environment, you end up with what we call the quantum master equation. But if you examine this equation, you have two terms. One is unitary evolution, and this is dissipator one. And as I mentioned before, the quantum gates are all unitary gates. So this part can be run on a quantum computer, where this one cannot be run on a quantum computer. And the question is, how do you run non-unitary dynamics on a unitary machine? So they have two ways to do it. One way, you said, OK, let me see if I can engineer the noise in the machine to mimic this term. And this is a hard thing to do, but this is an option if you can control the noise. The other option that what we have done is there is a mathematical theorem said if you have a non-unitary dynamics, you can do the dilation theorem, which means you increase the physical space and make it unitary. And this is what we have done. We took the term that is non-unitary, we increase the space or the dimension of this matrix and make it unitary in order to run it on a quantum computer. And as a simple example, we took the two-level system. This is the spontaneous emission. It's a simple system, but also to solve this one, you have to run through the quantum master equation. And we were able to show that one can run and look at the spontaneous emission on the IBM machine. The solid line is the exact results, and these are from the machine, from the real machine. So you can see in principle, I can take non-unitary dynamics and make it unitary and run it on a quantum computer, which will give us an opportunity to run open quantum dynamics on these quantum machines. And of course, what we have very complex problems that still need to be solved, like photosynthesis or improving the efficiency of solar cell. All these are very complex systems. And hopefully with machines with more qubit, we can run the quantum machine, the quantum master equation. I would like to end here with another problem that we are using to control the outcome of chemical reaction, which has to do with the entanglement. So the concept entanglement, so I explained before the superposition, interference, and this is the third one we use in quantum computing, quantum information, is the concept of entanglement. And the first one to introduce this concept was Schrödinger back in 1935, and he defined it this way. For an entangled state, the best possible knowledge of the whole does not include the best possible knowledge of its part, which means if I have two subsystems A and B and put them together, they lose their identity. And mathematically, you cannot factor the wave function of the whole system into A times the product B. So again, you put two A and B together, they lose their identity. And this is what we call entanglement. But what was the exciting about it? If you still separate them to a large distance, and you do measurement on one, and you put one here, for example, on Earth, and one on the moon, and you do measurement on this one, you determine the state of the other one. Of course, Einstein did not believe in this phenomena, and he said he called it spooky action at a distance. And he said the quantum theory is not complete, and there are hidden variables. And he died with in the 50s and did not believe in this entanglement and continue arguing that our quantum theory is not complete. But we know that entanglement exists in quantum mechanics, it's a true phenomena, and people have done experiment, what we call a quantum teleportation. They started experiment back in the 70s and 80s on the lab with a small distance, and slowly with the improvement of instrumentation, they were able to reach, like in this kind of experiment was published back in Nature. They did quantum teleportation, which means they teleport quantum information from one side to another, and you look at the distance, it's 143 kilometers. So it's a true physical phenomenon. It's not like it's not just from quantum mechanics. And of course, in 2017, the Chinese group also published back in Nature ground to satellite quantum teleportation. And if you look at the distance, it's 1,400 kilometers. So you can see there is still debate about the efficiency of this process, but at least in principle, the experimentalist can take this entanglement or the quantum teleportation from a small distance to a larger distance. So back in the 64, John Bell developed what we call the Bell's inequality, which he showed if you have two parties, Alice and Bob, and they have two different apparatuses doing measurements, and he showed if you have an entanglement between the two, if you have entanglement pair and you put one here and one here, they violate this inequality. But if you don't have entanglement, they don't violate this inequality. And just a couple of months ago, with my students, we were able to generalize it from discrete measurement into continuous measurement. And the focus was on the outcome of the scattering of chemical reactions, where you look at the distribution as a function of the scattering angle. And we were motivated by two experiments in this field, by the experiment done in Yang Shin group, and he looked at the interaction between two rubidium atoms, and he called it the quantum chemistry interferometry. What they have shown in this experiment, for certain superposition of the spin state, you have an outcome, which means you go to the excited state, and other superposition, there's no outcome, which means you have two paths with the interference, one destructive and one constructive. And for certain combination, you can control the outcome of this chemical reaction. And again, there's another beautiful experiment by Dick Zare group, where they look at the scattering of HD from H2, and they can control also the rotational quantum numbers, and they can see the difference in distribution if you scatter with this way or scattering with this way. And we design what will the measurement needed to show if a quantum entanglement exists in the outcome of chemical reaction. And for Dick Zare experiment, we still need another two measurements to show the results. And we know that they are working on this one to complete the two measurement into four measurements, so you can check the results. So far I talked about superposition, interference, and entanglement, and people ask us, what do we do for fun? And when we have time, we play quantum tic-tac-toe. So if we go with the classical tic-tac-toe, we have two players, and each player will do one move. But the quantum version, still you have two players, but each player will do two moves at the same time. So you have, see here, x1, x1, O2, O2, x3, x3. And a couple of years ago, with my former PhD students, we wrote two articles in Journal of Chemical Education, trying to explain all these concepts, like entanglement, interference, superposition, all this in this game. And at that time, Bill Bailey was the chemistry outreach coordinator. He organized a workshop. He brought to Purdue all the high school teachers in science. And we introduced the game, and they took it back to the classroom. And I think they're having fun. Because, I mean, just like here an example, the way it works, like if you have x1 and x1 here, and you decided to do measurement here, once you do a measurement, the system collapses. So you have x1 here, you have x. But once you have x, there's no x here, there must be the results O here, and then x, and you continue. You have many options. And then you can play it more than 3, you can increase the size. And there is a lot of fun in this game. But when I took it back to my kids at home, they said there is no fun in playing this game. So this is really an exciting time for quantum information computing, and this report from the Home Security Research, they show that by 2024, the quantum computing market will reach 10.7 billion. So there is a lot of investment with many companies in this field. And hopefully I show you that in chemistry, if we know how to do structure and dynamics on these machines, hopefully in the future, we're still at early stage, but hopefully in the future we have enough qubits or good qubits, we will be able to go for exciting problems in chemistry and see if we can do the structure and dynamics of these complex systems. So just to summarize, today most experimental chemists rely on calculations performed by computational packages such as GAMES, Gaussian, and many other packages. And we are quickly reaching our limits. For the next revolution might lie in the design and generation of quantum computers. So today, all chemists are using these computational methods based on classical computing, and hopefully in the future, we'll have both classical and quantum. I would like, at this point, to thank my also colleagues at Purdue. We have 4 exciting projects, with Andy and Chi about quantum simulation with the qubit using their photonic qubits. That's an exciting project. Instead of working with 2 qubits, we might be able to do the simulation with large number of states, what we call the qubits. We have another exciting collaboration on quantum machine learning for data analytics. With Ashraf, we are using for optimizing the solar farm. With Alex, we're looking at the stability of the grid. And with Andy, we're looking at high energy results. And all these projects are involved large data. So each day they collect data with the petabytes. It's 10 to the 15. No classical computer can manipulate this data. And hopefully with machine learning, we can make our progress. And of course, we have the grant with Young and Libai about quantum entanglement and quantum coherence in complex materials. And we have also one project to see how to implement the quantum random access memory on a photonic setup with Sasha and Vlad. And I learn a lot from my colleagues, and hopefully we'll continue with this project and see how quantum information computing can help us in making progress in these projects. Of course, I would like to end thanking my graduate students and postdocs. They are here back in the back. And I was lucky to have students from computer science, physics, engineering, and chemistry working on different aspects of quantum computing. And of course, the different agents for funding, NSF and DOE. And I would like to thank you all for your attention.
Even though we're about out of time, we do have probably, if Sabri's willing, to take a quick question or two. Any question?
What kind of training do you think that students and postdocs and young people getting into this area need? Is it a basis with chemistry and then extra mathematics and physics on top, or is it more coming from the computing, theoretical computing, or mathematics side first?
So this is the most interdisciplinary research, because you have people from math, computer science, physics, chemistry, engineering, and many universities that try to come up with a degree in quantum engineering. And I think maybe Vlad, we discussed it here at Purdue. So you need also an undergraduate degree in this kind of material that students can take from engineering, physics, math, all this, and prepare the students for this new revolutionary ideas. So quantum engineering degree would be great if we have it at Purdue.
Actually, I have 2 questions, but I had to choose one. So I'm going also for the nasty one. So chemistry appears to me like the worst possible case for quantum computing, because you have a very well-established competitor density functional theory.
Yeah.
At the moment, what we have is not a density functional theory, but poor man's density functional theory. You don't have the original Hohenberg DFT. You have this fictitious orbitals, so you're back to solving Schrodinger's equation. Imagine that we finally, by some great discovery, get the true density functional that was promised in the 1960s. And then every quantum chemistry problem will be reduced to finding a single classical function of three variables. So are you either in this community, either believe that this will never going to happen, or is it that you think that quantum performance, which you're basically solving much harder problem, finding lots more information than density, do you think that has a key advantage which will still allow you to kind of be the winner in the future in this case?
To answer this question, usually, like what we do in quantum chemistry calculation, when we do the scaling, we say DFT, people do with linear scaling and so on, and Hartree focus in the fourth. We don't count the worst cases. And there was a theoretical study showing that finding the universal energy function in DFT is an NP hard problem. So, I mean, usually we don't discuss the worst cases, we discuss the best and how do we scale things. So as you know, like in the Homberg-Kohn theorem or the Kohn-Sham, we don't know what is the universal energy functional. So what we have done over the years, we do approximation after approximation. So you know, like if you do material, you look for a trend with the density functional theory. Sometimes you predict the gap, sometimes you don't predict it. And this is because we don't have a universal energy functional. If some people try to use the quantum algorithm to find what will be the universal functional. But if you know in this field, I mean, people here also doing DFT, we have over 100 different functionals. People fit it to so
Not a single one of them is right.
Yeah, so I mean, if we get to this point where we start doing approximation after approximation, we lose the powerful approach of this quantum computing. Until we figure out what is the universal energy functional, then we can map it back to a quantum computer. But I agree with you if we can do it, yeah.
Thank you.
Okay, well, please join me in thanking Sabri.